our last section in chapter 6, slope fields. All right, so some synonyms for slope fields. Okay. Anti-differentiation. Indefinite integration, or solving differential equations. Okay? Basically, a slope field is a graphical representation of all of these. Okay? When we take an indefinite integral, we get technically multiple answers, correct? The antiderivative of x is 1/2 x squared plus c, all right? That plus c could be anything, right? And so graphically, we have a lot of different parabolas that we can draw, right? And an infinite amount, right? Okay. Now, here is where slope fields are going to be helpful. Okay. We're going to look at slope fields for any kind of differential equation, but where they're going to be the most helpful is when we can't actually separate our variables. So on Tuesday, we worked with something like this where we can separate the variables. Okay, sometimes we're not going to be able to separate the variables, and the slope field is basically going to be the only thing that we have to see the patterns in what our actual equation would look like. Okay, so a slope field is basically a graphical representation my handwriting is not really awesome with this, I'm sorry. Of a general solution to differential equations. Okay, and I'm going to put diff-EQ just to save some room up here because I have to write a lot larger than you do. But a slope field is a graphical representation. Good morning. Okay. Okay. Thank you for warning me. Thanks. Okay. I would like you to discuss at your pods, what does it mean when I say dy dx equals x squared?
Every x, y, 30 x squared. I guess. No. No. I formulated this in my own way.
Okay. All right. Pod 3. What did you talk about?
I was going to say antiderivative of.
Okay. Pod 1. What did you say? Whoops. Anything, Pod 1?
No.
Nothing. What does dy dx mean? Derivative. The rate of change is x squared. What's another word for rate of change?
Derivative.
Okay. Give me another synonym.
A. Slopes.
Ah.
So for every.
Since this is describing the derivative, then for any point, we know the slope is x squared.
No.
Okay, so here I have a grid for you. Okay, and what we're going to do, we're going to draw itty bitty tangent lines at each of these coordinates, representing the slope at each of these coordinates. Okay, so dy dx, I'm going to write it right here because it's gone from where you can see. If dy dx is x squared, what is the slope at 0, 0?
0.
So we're going to draw an itty bitty tangent line with slope 0 at 0, 0. What about at 1, 0? What would our slope be? What would it be? When we plug 1, 0 into dy dx, what do we get? 1 squared, right? So at the coordinate 1, 0, we have a tangent line with slope 1. I'm going to draw just an itty bitty tangent line there to represent that. Okay. We're going to keep going here. 2, 0. What slope does it have? When I plug x is 2 and y is 0 into x squared, we get what?
4.
4. So now we have a really, really steep tangent line. We're going to do this for every coordinate. Excuse me, every coordinate. Okay? Now, since our derivative is only defined in terms of x, this is going to be a little more simple, right? What would our slope be at 0, 1? 0. Because I'm plugging 0 in for x and 1 in for y. We get 0 squared. What about 0, 2? X is 0, y is 2. What's our derivative? 0. It's going to be the same for 0, 1 and 0, negative 2. All right. How about the coordinate x1? X is 1, y is 1. What's our derivative? 1 squared. What about the coordinate 1, 2?
1.
Okay. 1, negative 1 and 1, negative 2. Those are all going to have slopes of 1. Okay. The coordinate 2, 1 will have a slope of 4. The coordinate 2, 2 will have a slope of 4, etc., etc. What about the coordinate negative 1, 0? What kind of slope will it have? 1, because we're plugging x is negative 1, y is 0 into the derivative. Same thing with negative 1, 1, negative 1, 2, negative 1, negative 1, and negative 1, negative. Okay? Anytime x is negative 2, since there's not a y here, what's the slope going to be? The slope's going to be 4. Okay? Here's our slope field. Okay, it's a graphical representation of a solution to a differential equation. Now, let me ask you this. If I asked you for the antiderivative or the or I asked you to solve the differential equation dy dx equals x squared, what would your answer be? 1/3 x to the third plus c. This kind of looks like a wind map in my mind, okay? When we like follow the wind is what I'm going to describe it as. What kind of function do these little tangent lines create? What function goes like this?
An x cubed.
Oh, an x cubed function. Okay, so when we graph our slope field, it's going to give us whatever curve the solution to the differential equation would be. Okay, if we pick any of these points for our initial condition, we could draw a lot of different cubic functions here, right? We can draw one here, we can draw one here, we can draw one here, okay? But the point is that it represents the infinite number of solutions we have to a differential equation. So since our antiderivative would be 1/3 x cubed, we have a bunch of cubic functions here. 1/3 x cubed plus c. That kind of cool? How it does that? Okay, let's look at another one that has x and y. So next page. Okay, the first thing we need to do is graph all of the tangent lines for this coordinate plane right here. Okay, so I've given you a lot of coordinates. All right, so we have y prime is x plus y. So I'll get you started and then I'll have you continue on your own. So x plus y is our derivative. So at the coordinate 0, 0, what is 0 plus 0? Okay? And then if we would go to like the coordinate 1, 0, what is x plus y at the coordinate 1, 0? 1. Okay, let's get something a little bit more interesting. At the coordinate 1, 1, what is x plus y? 2. So at the coordinate 1, 1, we have a slope of 2. So it's just a little bit steeper. Okay, I would like you and your pod to work together and get all of these slopes for this slope field. You will see some patterns because of the x plus y. And if you pick up on those patterns, please use them. Do not move to the next example without me. When you have your slope field completed, just stop and wait. Okay, good. Keep going. Okay, here is my slope field. Please compare it to yours. Does it look the same? Yes or no? Look the same? Okay. Since we have this x plus y pattern, did you like notice a pattern along the diagonals? Right? Okay. That was kind of nice. Save you some time. Okay, hopefully you can find some patterns when you are creating these slope fields. All right. So this is a differential equation that we could not separate and solve. Okay. So this is one that we have to look at the slope field to be able to see what kind of original equation we have. All right. Now, it is asking us to sketch the graph with the initial condition 0, 1. So 0, 1 is right here. So our curve needs to go through that coordinate and follow a path given by this slope field. Okay. Now I'll tell you, anytime you have these little tangent lines that make that you can see like a line, like these would all connect and basically act as an asymptote. Okay. I see that this diagonal, they all have slopes of 0. So when I come this way, I know at some point I'm going to have to switch directions because of those 0 slopes. Okay. So basically you're just going to let the wind take you in the direction you need to go. So we know that at some point here we have to have a slope of 0, and then our slopes have to be negative over here. This is acting kind of as an asymptote. And then here we get steeper and steeper and steeper with our slopes. Okay. If I gave you a different initial condition, we would have a different graph to make. I could give you an infinite number of initial conditions to get a different graph, but we'd still follow this same slope field to get a pattern. Okay. Okay, so we need to practice 2 things. We need to practice looking at slope fields and determining what their solutions are, and we need to look at slope fields and determine what their derivatives are. Okay, so our first task, which is right below there, these are 2 differential equations, and their general solutions are down here. Take about a minute and a half, and as a pod, come up with which general equation represents which slope field. So there's only 2 down here that match the 2 slope fields. Okay, one answer for each. All right, let's come back together. Pod 2, what do you have for number 1? That's you. Yes. Why?
No, I'm just kidding.
Who would like to explain it? Okay, if you take derivatives and plug in points, you get those slopes. Another way to look at it, This looks like a sine curve, right? So that would be the solution, okay? Part 4, number 2. What? D. D, and why is it D? Okay, it makes a cubic function. And D is a cubic function.
Doesn't it have asymptotes though?
I don't think those are completely straight. They look like it, but I don't think that they are. Okay, it's kind of deceiving. All right. All right, so now, this is probably the easiest way to identify a slope field. If we have the general solution, the slope field should have a rough picture of what that graph is, right? Now, if you turn it to the next page, here I have slope fields and I have their derivatives, okay? Now remember, we use derivatives to create the slope fields, okay? Like we had dy dx equals x plus y, and that's how we got our slopes. So now take a couple minutes with your pod and match these 6 slope fields with the 6 differential equations.
Whatever this wasn't the
Because there should be getting steeper before they make a round. But like, it should be getting steeper like this.
Yeah.
And then all
So
this thing.
we're using them all.
Cause like, yeah,
It's just
but
harder
it's
to tell.
right here.
Like,
Cause it's still.
would that be?
I agree with you. I do. Because x divided by y, anytime like x is 0, you're going to have horizontal, right? Anytime y is 0, you're going to have vertical. So that happens right there. And then anytime x and y are the same, you're going to have 1, right? Anytime x and y are exact opposite, you're going to have -1. All right, your answer should be number 1 matches with F, number 2 matches with C, number 3 matches with A, 4 B, 5 E, and 6 D. Any discrepancies there? Okay, I always like to look for patterns like this 2 minus y. Since it solely relied on y, you're going to see horizontal patterns, right? It doesn't even matter what x is, so you're going to see patterns across. If you have one that solely relies on x, you're going to see patterns straight up and down, okay? Like b, right? E to the x, what's the derivative of e to the x? E to the x, what's the antiderivative of e to the x? Okay, antiderivative is e to the x, so it's still going to look like e to the x. Okay, get the easy ones out of the way first when you're matching them up, and then work on the other ones. Okay, so let's go to your last problem. want everybody to take 2 minutes and fill in the slope field for, what is this, x, y divided by 2.
Yeah, how do you draw 1/2 this one?
Well, just think of like 1/2 is like up 1 over 2.
Yeah.
So think of it like that. One more minute.
What'd you mess up?
Okay, look at mine, compare it to yours. Are they the same? What's the first thing that you did when you graphed these slopes?
Zeros.
Go to all the ones that are 0, right? Get the easy ones out of the way first. That's kind of my philosophy. Okay. This is an AP question. They give points, typically 2 points for a slope field. 1 point for all the 0 or undefined. In this case, there's 0, and then 1 point for all the other ones. Okay. All right. Then in part B, they ask us. In part B, they ask us to write the equation for the tangent line to the curve through the point 1, 1, and then use it to estimate the value of 1.2. So this is just a tangent line equation. This is like Unit 2 stuff. Okay. So for part B, if we're going to write a tangent line, what do we need? What? What do we need for a tangent line? We need the derivative. So dy dx, we need to evaluate it at the coordinates 1, 1. Which is what? 1/2? So our coordinate is 1, 1. We have determined our slope is 1/2. So we have y minus 1 equals slope times x minus 1. There's our tangent line equation. Okay. Now, if we want to approximate the y value of 1.2, what are we going to do with that? How do we approximate the value of x is 1.2? I just gave it to you. What do we do with 1.2? Thank you. We plug it in for x. So we have y minus 1 equals 1/2 times 1.2 minus 1. What is 1.2 minus 1? 0.2. And what happens when we take 0.2 and multiply it by 1/2? 0.1. And then so we have y minus 1 equals 0.1. So we get approximately 1.1. Okay. Because we're using the tangent line to approximate it, it's not on the actual curve. Okay. All right, so now for part C, we're actually going to find the particular solution and then plug in 1.2. Okay? So this is what we did 2 days ago. Oh, I'm just kind of struggling here. Okay? So we need to do a separation of variables. We have dy dx equals xy over 2, right? So to separate variables, we can divide the y over and multiply the dx over. Okay? We have about 4 minutes left, so I'm just going to kind of do this without asking you for your help, okay? So the antiderivative of 1 over y is the natural log of y. Antiderivative of x over 2 is going to be x squared over 4, and then plus c. Since we have that natural log, we're going to have to take e to the left side and e to the right side. E to the natural log cancels out, and so we have y equals e to the x squared over 4 times e to the c, which, yes, is just going to be c. How do we figure out what c is? Do we have an initial condition? Yes, we do. We have the initial condition of 1, 1. So if we plug in 1, okay, we get 1 equals c e to the 1/4. Divide that over, and c is e to the negative 1/4. We have e to the 1/4 in the denominator. That's like c to the e to the negative 1/4. Okay. So this becomes y equals e to the negative 1/4 times e to the x squared over 4. Okay. And we know that since we're multiplying, we can add those exponents together. Okay? With your calculator, we can actually now plug in 1.2 to get what it really would be. And I'll just tell you, you guys know how to work your calculator, is 1.116. Okay? Now, when we use the tangent line, we got 1.1. Is that an over or an underestimate? It's an underestimate. Let's go back to our slope field and talk about why it's an underestimate. Here is the coordinate 1, 1, which means we would have a curve like this. What's true about the concavity at 1, 1? It would be concave up, which means our tangent line is sitting underneath our curve. Therefore, our tangent line is under approximating our value. Okay, we'll do a little bit more with that tomorrow in our AP problem, but this is the homework that I'd like you to work on tonight. I'm not going to post answers today. We'll go over answers tomorrow in class, but you need to have this completed. Happy Thursday, you all.